So when we did thermodynamics, we would have a chemical equation, and along with it, we would keep our heat right next to it. And then, like, if we reverse the reaction, we change the sign of the heat because it's the endothermic, exothermic. So I like to do that in these sections as well, where instead of keeping that thermochemical equation, that heat with it, I'm just going to write the K that goes with it. Because if you have that K expression, then it's just easier to see to start with. We tend to start to get some mastery and want to jump ahead really quickly and not show work. K equilibrium is going to be the products to their coefficients over the reactants to their coefficients. A little out of room here. So, and I've got tons of space here, so I might as well just rewrite it. But I tend, in my work, I like to keep it with the equation. We'll see why in a couple minutes. And it's in terms of concentration, so we might also call it a Kc. And then we're going to check this out for each trial. Trial 1, trial 2, and trial 3. So we're going to get 3 different equilibrium constants and compare them. This is pretty detail oriented. It's easy to forget your exponents. It's also handy if you have the squared button on your calculator to use that rather than a bunch of parentheses and writing down intermediate values.
The concentration of NH3 is squared?
Yeah, see that coefficient of 2? Yep, all the details.
0.06025.
Yeah, that's what I got too. Okay, let's do trial 2 and trial 3, and what do you expect, and what do you get?
Should be the same or about the same.
Yeah, we expect it to be the same.
Yeah, it's pretty close.
And I got 0.60219. Yeah, so they're matching in that decimal place. These ones are much higher concentrations, right? But at equilibrium, we should get the same K value. So again, if we rounded to the third significant figure, that would be the same. So we have different starting points for our equilibrium. Like this one started all as products. This one started all as reactants. And then this one had a balance and pretty high molarities. They all give the same K, so yes, they should be. Heterogeneous equilibria. In this example, we have the liquid and the gas, or the solid and the gas. So that's what we're talking about with heterogeneous, the different phases of matter. So when we have something that's a pure substance that is either a solid or a liquid, basically the concentration doesn't really matter. It's kind of like it's either there or it's not. So they don't come into the equilibrium constant at all. When we look at this reaction down here, that eggshell reaction, the calcium carbonate, if you have eggshells, right, and they were going in the forward direction, it would decompose. If there were no eggshells, there would be no forward reaction, right? So it's kind of like, that's conceptually how I understood this. This reaction is governed exclusively by the gas, by the pressure of the gas. So here's a picture of that same reaction. And they're measuring the gas pressure with this manometer. It's just a closed tube with mercury in it. So then we get that difference in the height So notice in that picture that the calcium carbonate piles are different sizes and the calcium oxide piles are different sizes,
Mm-hmm.
and yet the pressure of CO2 is the same. That equilibrium for that closed system depends only on the pressure of CO2. It doesn't depend on the solids. So they do not come into the equilibrium expression. We'll just leave them out. And that means for, oh yeah, if it's a pure solid or a pure liquid, the density is constant. The density is like the concentration of the mass there. Its molar concentration is also constant. So for example, water I think is like 15 molar or something like that. And so if you take away 0.01 moles, it's essentially still 15. If there's water, if there's pure liquid, that molar concentration is relatively constant compared to the other reactions going on, the other species involved in the reactions.
So we really only consider the aqueous, I guess, in a liquid solution.
Yeah, gases and aqueous both come into our K value.
And we just ignore everything else, basically.
Yep.
Oh, that's awesome.
Mm-hmm.
Yeah, it is. So here we go. This is just using the math to show you about those concentrations. C is representing the molarity, basically, but molarity for a solid seems weird. It's more like a density. Anyway,
Yeah.
we cancel out, and we end up with that equilibrium depends only on the gas. So we will write Kc.
For Kp, I know when we calculate it from Kc, we multiply RT to the delta N. When we look at this equation, it has gas on one side and liquid on the other. When we think about delta N, do we include that liquid? So would it, be like -1 instead of like -3?
No, it's going to only be, so let me write down that equation. Now, I'm not sure we need to use it right now, but
Sorry.
P equals Kc times RT to the delta N, where delta N is moles of gas in the product minus moles of gas in the reactant.
Oh, yeah.
So moles of liquid water would not come in at all.
Okay, so it would be -3 in this case.
Yeah,
Okay.
that's right. So I might just write this as the expression, right? It's asking for the expression here. I'll write a Kp. There's no gases on the reactant side, so it's 1 over pressure of hydrogen squared times the pressure of oxygen. The Kc would just be those concentrations. So if we had a value for one of those things, we could calculate the value for the other one using that equation.
Mm-hmm.
But this would be to go between those values. So just the expressions, we're just looking at the K expression itself. So again, the solids don't come into play, it's just the gas. And I think we have one more, right? Yeah, there it is. Now, here we get, I don't know if I've talked about units magic yet. This is part of what I call units magic. Okay, so that's where we start talking about the activity instead of the concentration. Basically, we want to be able to work with this thing that would have different units depending on what goes into that expression, right? Looking up at these guys. But in order to get rid of those units so we can put it up in the exponent or in the log and all of this, we're going to divide everything by its standard state, which is like dividing by 1 molar. Or if it's a gas, we divide by 1 atmosphere. And that cancels out the units. It seems like, so some students who really pay attention to the details are very bothered and they think this just doesn't make any sense. How can you just do that? And other people are like, what a relief, I don't have to worry about it. It seems like it might cause problems later, but it doesn't. So that's why it's magic. It also has to do with looking at things in this dimensionless viewpoint. We're always normalizing to a standard.
It kind of makes sense because these equilibrium constants are a ratio, kind of.
Yeah.
So
And
it makes,
if you were literally looking at the units, like these two values would have, like this value,
oh yeah.
this value would have different units, and how does that make sense? So we're not going to worry about the units on K. We're going to
Okay.
assume their activities, which is like a special kind of molarity that has been normalized to 1.0 molar at standard state conditions. So we'll call them unitless. So let's take a look at this problem. We have a new equation. It's got all gas phase. Looks like we're going to work in Kp for this one. We are given an equilibrium mixture set of values and a total pressure. So let's see, we've got values for methane, hydrogen sulfide, hydrogen. So that total pressure is how we're going to get pressure of CS2. Did you get that same value for the CS2?
Yes.
The 0.52 atmospheres? Yeah.
4.16 to the minus 3.
Yep.
That is our Kp. So when we calculate Kc, oh, I'm going to rearrange this equation up here. Kp over RT squared all right, so then that value is off. All right, so it's smaller. And the next one. So for this one, we want the concentration of chlorine at equilibrium. So we're given the CO, so at equilibrium, and I like this little symbol in my own work. I don't always use that, but it's like a Mobius that doesn't connect, and then that's how in my notes I just have at equilibrium. So we have 0.012 molar, and we've got 0.14 molar, and we've got our Kc value. So of course I'm going to write my expression. And then I'll plug in these equilibrium concentrations. And it has to be molarity. Probably just 2 sig figs based on the other ones. Okay, here's another one. This one is like a Kp. right? We're going to need the Kp because we're looking for the partial pressure of CO2. That's what we're looking for. Notice that we are not given that initial amount. But that's okay, we don't need it because the Kp expression is PCO2 times PNH3 squared, and then that's a solid. So that doesn't come into the equilibrium. So we don't have quite enough, we don't have our Kp value. I was thinking we had our value, we don't have that. So we have to figure out what do we know that can allow us to solve this. Getting kind of creative algebraically. So we have some amount, we have some excess of this solid, and it's going to react here. For every CO2 molecule, how many NH3 do we form? For every X that reacts away, we're going to get X CO2 and 2X for the ammonia. At equilibrium, this is 0.242 atmospheres. 0.242. Here we want to know how many atmospheres. So we can use this part to figure out what is the pressure of CO2. Here, 2x equals 0.242 atmospheres. So x is the pressure of CO2, 1 atmospheres. And then our Kp is going to be the product of those. Tables, have you done stoichiometry with tables like this before? I like to introduce them early. Sometimes this is the first time students have seen them. When we do equilibrium, we really kind of need the ICE tables, or sometimes they're called RICE tables, or there's lots of names for them. But basically there's an initial given amount, some given value in the problem. So if I start with grams, I usually like to convert that to moles, just to make that clear. Then there's the change during the reaction. And we use that right here, right? That's kind of what I was getting at with this equation, the x and the 2x. So this is going to lay everything out into columns, so you don't have to worry about the labels. And the change is going to represent what happens during the reaction, and the equilibrium is our final concentrations. So the changes that happen during the reaction depend on the coefficients. In this case, initially we have 0 ammonia. So clearly the reaction is going to go from left to right, right? So every time one of this reacts away, 3 of these are going to react away. And at the same time, 2 of these are going to form. We have to solve for these values. We have to solve for these values in order to write Kc. So how can we do that?
We can multiply the terms in parentheses together and get all of the x's on one side and all of the things without x's on the other side of the equation.
Yeah, that's going to be a pain.
It is.
We might have to solve for x that way if we were given Kc, but looking at the table, we can see a quicker way to solve for x.
Oh, is we use the NH3 because 0.25 equal 2x.
Yes. So 2x is 0.250 molar. So x equals 0.125 molar. That's called, you know, in the old school way, this is called the reaction equivalent. That's the x value. So I can plug that in here, right? I can say this is actually 0.235 minus 0.125. And now I've got a value. And then similarly, we'll plug that in here. And that'll be a 0. Because we have 3 decimal places. All right, so KC. We're going to use the equilibrium values to plug in here. So make sure you're reading the correct line. I didn't write my expression. I've advised already that you always write your expression because it can help you catch errors. But then I just totally didn't do that. So 0.08154. So these come in all kinds of forms. We have to get a little creative about how to solve them. So we'll just be really careful identifying what we're given. So we have our initial mixture. And, oh good, we have 1 liter. So all of those mole values we'll just write as molarities. Then when equilibrium is established, we've got 1 concentration. So let's lay that out in our table. That's a molarity. That's a molarity because it's in 1 liter. And we're going to start with a little bit of water. And yeah, there's no nitrogen initially.
Which so it's not mentioned, it means 0?
Yeah.
Uh-huh.
All right, so the NO at equilibrium now we'll use the coefficients to write that change. Minus 2x plus x plus 2x. And then those are going to give us our equilibrium values. So from this section, we get an equation we can solve. And then we're going to plug that back in all around. You guys getting an answer?
Got 653 down. Yeah.
Great. Okay, so we're just about at the end of our time, so we'll stop there. Finish this one up next time. For our quiz tomorrow, we have basically wrapping up kinetics, mechanisms. What's fair game for the quiz tomorrow? So as far as equilibrium, we'll basically just write equilibrium expressions or maybe calculate equilibrium expressions. I don't think that the sections in the book communicate it that clearly. So this is chapter 12 and 13, the start of that. We have mechanisms and catalysis and energy diagrams from chapter 12. So this is from chapter 12. And then chapter 13, probably not as much. So writing K expressions. We haven't even really quantified lying to the right or the left. That makes a little more sense when we've done some work in those quantitative calculations. But what else did we do? Oh, just solving, just writing the K expressions, solving for K or concentration, pressure, given values. It's probably going to be weighed more towards chapter 12.
Can you go back to the example 5? Like I was kind of curious how you got like 600 something.
Oh, I was just jumping ahead to the answer in case anybody was ahead of me, which I figure probably some of you guys are working faster than I am. So we have to plug this in. We know that the Kc is H2O squared N2 over NO squared H2 squared. So we have to plug in this line of concentrations into there. Wait, 019 is X, and there's 2 of them, and we start with 1 mole. Yeah, I'm getting a different value for the water.
Wait, you're adding it, not subtracting.
So this is 0.138, 0.138.
When you add on 9 molecule of SO2 and 9 molecule of CO2, is it still the same, the ratio?
It ends up the same.
Okay.
So that's similar to this question. Well, here's a graph.
Mhm.
Whether we start up here or down here, the final concentrations end up the same.
Okay. Okay.
Yeah, and that was the same. We looked at that again with this first table, this one. All these different kinds of calculations, all these different starting points all end up with the same K.